Okay, well, welcome to this initial video on the Confirma IC design system. My name is Kevin Faison. I'm a longtime IC designer, and I'm the developer of this software. In this video, I'm just going to give the very first view of what I consider to be a prototype but still stable version of the software that I think is getting pretty close to public release. So what is Confirma? Confirma is a design system and framework that is composed of a variety of low-cost point tools that have been knitted together to create a easy-to-use and coherent design flow for the purpose of designing custom integrated circuits, mainly circuits that involve RF, analog, and mixed signal circuitry. It may also be used to design math-based behavioral systems and subsystems, much as people do today, using tools such as MATLAB Simulink and other kinds of system simulation software like SystemView. It's intended to be very low cost, again, very easy to use. It's suitable for individual designers as well as for design teams or university research teams. Confirma has, in fact, been used in team environment for many years to design pretty complex ICs such as 4G cell phone transceivers, LiDAR receivers, lots of RF power amplifiers, IP blocks for Bluetooth transceivers, SerDes IP, as well as catalog power management chips. So it's been used within a tier one semiconductor company. It's been used in research centers, and it's been used to design quite a lot of chips for international customers. Um, it's always been a system that has been captive, however, so it's never been released to the public. So this will be the first version that will be released for use by the general public. And one of the reasons this is now possible where it wasn't before is there's quite a lot of good quality, excellent quality, open source type software point tools that we've been able to leverage to make this happen. So one of the point tools and important point tools is Kicad schematic capture. So we used to use a Mentor-based tool that was kind of expensive and has some limitations. Kicad has come along. I guess it's been under development for something like 25 years. It's very popular with PCB designers now. It's very high quality. It's easy to use. So we've ported the Confirma design flow in such a way as to leverage KiCad as the design capture front end. There's also a variety of SPICE simulators that are available now that are very high quality, low cost. NG Spice is a popular one, as is Zeiss from Sandia National Labs. That works very well. There's some paid Spice simulators that are modest cost. Top Spice works very well. That's one of my favorites. There's also waveform processors, things like that. These tools can all be plugged into the Confirma framework. So you can plug different tools in, but the framework and the flow does changes very little. So as new tools come along, you can plug them in, more powerful tools, you can plug them in, but you haven't changed the design flow very much, and you haven't lost access to your pre-existing designs. You'll always have access to your KiCad schematics. There's no licensing involved, so you'll never lose access. And so that's very, very good. Okay, so I think that was enough talking. So let me go ahead and get started here with some examples. So on the right-hand side, you have what is the Confirma cockpit. And so the Confirma cockpit, it interfaces, it interacts with KiCad and SPICE simulators to enable this complete design flow. So I'm going to try and give you some demonstration of how that works now. Um, I have I already have an existing design up, but I'm going to switch to a different design. So I've got two different simulation test benches, two completely different designs that are loaded up in KiCad, and I'm going to switch from this one here, this first one, and I'm going to switch to now to this one, which is a test bench with a transistor level OTA. And the reason I'm doing that is because I just want to show how you switch from one design to another design and how you do that and how that happens very quickly and seamlessly. So I'm going to do this pass to Confirma command. So there's patch software that I've loaded into KiCad. I'm going to execute this pass to Confirma and include the path. So I'm going to hit generate here. Okay, so what's happening is that patch software is passing over the schematic name as well as the schematic location, the path for where that folder is, where this design is stored. So it kind of does that in a slow-mo, so you can check for yourself that the information is coming over correctly. Let me close that. And let's see what happened here. So now within the Confirma design cockpit, you have T demo OTA. So that's actually this schematic here. And so let's take a quick look at what actually is on this page. So again, this is a CMOS transistor level OTA. This is the symbol for that. It's a hierarchical symbol, meaning that there's an underlying schematic. So you know that this is a hierarchical symbol with underlying schematic because there's this parameter that reminds you SCH colon. So that's how you distinguish that hierarchical symbol at a glance as opposed to these other symbols, which are spice primitive type symbols. So in addition to that, you have, so we have this circuit uh, prepared for spice simulation. So it has a variety of voltage sources to bias up transistors. There's an input pulse generator here. So we're going to feed this circuit with a transient pulse. Power supply is up here. Looks like we're running 1.8 volts. The OTA is configured in a feedback configuration. What we're trying to do is it's basically set up as a unity gain follower. So the output should track the input. That's the expectation here. And so that's the test bench. Since it's a hierarchical test bench, it's got hierarchy. Um, if you look, you'd like to be able to move up and down the hierarchy. So on the Confirma side, whenever you load a new design into Confirma, it automatically checks, searches for hierarchical symbols, and it lists those hierarchical symbols on this list box. So this is the Kicad sheet navigator, lets you move up and down the hierarchy. There's only one hierarchical symbol, but if you want to, you can go ahead and select that and then view that schematic. So this is the transistor level schematic that goes with that hierarchical symbol. So that's gives you an idea of how you move up and down the hierarchy. If there were hierarchical symbols on this schematic, then you could again move move down the hierarchy and uh, open up a schematic that might be present on that page. As it turns out, there is none. So if you move down the hierarchy onto this sheet, again, it searches for hierarchical symbols. There are none, so none are listed. So we'll move back up. So this gives you an idea how you move up and down the hierarchy. So you got these up-down buttons. You can select the symbol. You can view the schematics and so forth. So now we want to do a spice simulation. So what's normally required is you need a spice simulation netlist to send over to the simulator. Let me close this for a moment. So, so what has to happen is you have to extract that netlist from the KiCad schematics. So the way that works is there was already one up here. Apparently, I've already extracted it, but I'm going to re-extract it. So I hit fast netlist here. So you saw that little flash there. So just refresh that netlist. So Confirmer is gone, and it's it doesn't change any of the KiCad schematic files. It just opens them and it reads through and it looks for hierarchical symbols, and it digs. If it finds one, it looks at that schematic. It generates, it determines the hierarchy of the entire design, and then it figures out the connectivity within those schematics and up and down the hierarchy, and then takes that information and it converts it to the spice netlist. And that's what's shown here. So you got the spice netlist, and then this is the sub-circuit for the OTA. So you can see it says sub-circuit if you're familiar with spice commands. So this is the design represented in spice language that we're going to send to the spice netlist. Now, there's a variety of ways to drive spice simulators. You can drive them through by setting simulator forms. So there's pretty good compatibility, but not perfect compatibility across spice simulators. So this is a standard spice analysis menu where you can set up spice transient requirements, AC simulation requirements, output if you want to save all voltages and currents or just some, you set them up here. But there are some differences, again, in spice languages. And to deal with that, we have this so-called include tab here. And so if you want, you can type in directly into this include text file spice simulation commands. So for instance, here's a transient command for spice simulation. In fact, you can completely avoid setting simulator commands through the forms if you choose. So again, the reason we do this is because there are differences in spice simulators. So I'm going to skip ahead here and show various spice simulators that were set up to run. We're going to run these three here: Top Spice, Zeiss, and NG Spice. Now, if I click on these, there are some differences. So what's happening is the include file is changing a little bit to accommodate those syntax differences. But what's important is that the spice simulation netlist, the one that comes from the schematics, that doesn't change at all. And so what that means is you can still run separate simulators with separate differences in syntax using this methodology, um, but you can still do all that from the same set of schematics. So you don't have to have specialized schematics targeted to only one simulator or another simulator. You just have one set of schematics, and you can still run those various simulators. So that's very nice. It's very powerful. It saves you a lot of time. In fact, you don't have to, for instance, port your design to a different schematic capture program, one that's proprietary to the specific simulator. So that's very nice, saves you all that learning curve and all the time to port circuits back and forth. So it's very convenient and it's very efficient and quite it's a good methodology. Um, so okay, so I have Top Spice already selected here. We're gonna do the simulation. So I start Top Spice. Top Spice is loaded. It's checking the foundry models. It started the simulation. So I have the transient stop time set pretty long here. So we're not going to wait for that. So I'm going to go ahead and pause this. I'm going to say, no, let's not plot here. Let's stop the simulation. We don't want to resume. Let me get rid of that. So we're going to view the plots. We are going to view the plots, but we're going to view them through the Confirma framework. So hit view plots. And so what's happened is it's opened up the viewer that I happen to have plugged into Confirma, which is top view. It's the top view demo. So I'm going to hit transient. So you can download this top view demo software and run it. You can plug it into Confirma and run it if you like. So we're going to plot the input transient pulse wave, and then we're going to plot the output voltage follower waveform. So let's see what that looks like. So it's simulated successfully. It's read the foundry models successfully. And you can see those two voltage waveforms. One is the ideal input uh, pulse waveform, and the other is the voltage follower output waveform. And the OTA has finite bandwidth, so you see it overshoot and undershoot and finite rise and fall time, and so that's expected. But the main point is everything operated pretty smoothly, and we got the result we were expecting. So now we're going to switch simulators. We're going to switch from Top Spice to Zeiss, and we're going to hit sim netlist there, and now it should go to the Zeiss simulator. So very same circuit, we're running on Zeiss. It finished up pretty quick. Let's look for the in-output waveforms again. Here we go. Okay, looks the same. Great, that looks good. Okay, so now we've done Zeiss, and now we want to do NG Spice. So we're gonna hit simulate netlist. Now it's NG Spice. That went pretty quick. View plots. Go to transient, in out. Okay. And the simulation time was longer here. The transient endpoint was set later. So let's zoom up here. And it also looks about the same. So good news. So the simulators all seem to agree with each other. Again, these two, uh, NG Spice and Zeiss free simulators. Top Spice costs a little bit of money, but it also has some features that I like. I think it's well worth it. So, but it's nice to be able to run all those simulators from the same simulation schematics. And it's also nice to be able to view the outputs using a common waveform viewer. Okay, so that was an analog transistor level design, a very small and simple one. So now I want to switch over to this guy here. So let's take a look at this schematic here. So in this case, it's not analog transistor level, it's a lot of behavioral circuits here. So we have behavioral 5-bit A to D converter, or some kind of an input ROM table here, some kind of a logic gates. This is a block full of logic gates, some kind of a coder or encoder of some sort. And then this is a behavioral 5-bit DAC, it looks like. So as I recall, I think what we're trying to do is we're trying to generate a sinusoidal output wave using a D to A converter, and apparently there's some ROM logic here that encodes the D to A input, so we get a sine wave output. Then that sine wave output, which has quantization error, that's input to an analog filter, and so that should remove all that and give us a smoother looking analog waveform. So let's take a look at that. So what we need to do now is the old design is still in the Confirma framework, so we need to pass this guy over as we did before. So we're going to now pass this design into Confirma. I'm just going to say generate here, say OK here. All right, we're seeing the information. We can still, it's not too fast. We can read it. Looks okay to me. Okay, we're going to close this. Okay, so now, very good. So the test bench schematic has been loaded successfully into Confirma. And so we're going to do top splice simulation because I think this demo circuit is only set up for top splice. So if you look at the include file, you can see there's some SPICE simulation control statements here. Oh, but look, there's also some additional sub-circuits. So this looks like some sub-circuits, some logic sub-circuits. I think these are behavioral gates, a variety of behavioral gates here that are kind of unique to top SPICE, I believe. But the point is, within the include text file, you can have not only simulation commands, but you can go ahead if you like, you can enter in SPICE subcircuits using text if that's what you want to do. In this case, I think all this stuff has been auto-generated by some other software I'm not quite ready to talk about. If you look at the schematic netlist, the netlist that was extracted from schematic, this might be old, so I'm going to refresh this. So we'll refresh that. That was pretty fast. So this, all this SPICE uh, net listing, this all comes from this system here, this schematic system. In fact, let's take a look at what's on there. So let me just regenerate the hierarchy. So it's already got the hierarchy here. So you can see there's a variety of hierarchical symbols with underlying schematics. So let's take a look at what we have here. Let me take a look at that low pass filter. We'll pull that up. Here's the low pass filter. Let's see. What is this? Behavioral A to D converter. Let's take a quick look at that. Okay, so that has some additional hierarchical symbols on there. So what we're going to do is we're going to dive down onto that schematic page. So we're moving through the hierarchy, we're diving down, and when we did that, it again looked at the schematic and it found all the hierarchical symbols and it's listed them here. So these are these behavioral ADC stage things. And so you can see that they showed up. So if you again selected one of these and view the schematic, okay, so that's what's on what's in that behavioral schematic. So again, that's how you move up and down the hierarchy. We're going to go back up here. Mm, Something else to show, I think. So we're at the top level. Let me select this filter here. So one thing, when you're developing your system or circuits for the first time, you're hoping that you connect everything right, but you don't always do. And sometimes it's nice to be able to check individual blocks. So the CNet list thing, if you press that, that gives you the SPICE netlist only for that block. So if you're creating your symbol for the first time, you can check that your input output pins and your parameters are passed correctly. This is useful when troubleshooting, a circuit for the first time when you're first assembling. It's kind of a nice feature. This T netlist, that's for the top level test bench only. So if you click that, that's the top level test bench. So you can netlist these things individually as a part of a troubleshooting methodology. Again, if you want the whole thing, then you just do over here. So it looks like we're all set to go here. We've selected we do have Top Spice as our simulator, so we've got a refresh netlist. We've got our include stuff. Let's go ahead and simulate. Okay, so this could let's see how it starts off here. Okay, so while that is simulating, let me just pop over and let's take a look at the symbol library. So what I want to show here is so these are individual symbol libraries. So these are there's a variety of things here, but the main point is these are generally they're like hierarchical symbols. Some of them have schematics underneath. Some of them point to netlists that are kept separately in SPICE netlist um, model files. So if it says net here, that tells you that it's looking for that SPICE net list that's already existing in a SPICE model file. So let me go down here. Let's see, here's a logic thing. So apparently, so whatever this is looks to be an up-down counter. Now this says, it doesn't say net colon, it says SCH colon. So what this means is this symbol has an underlying Kicad schematic. So this works very much like it does in Cadence or Mentor Graphics tools. So you have a variety of building blocks. They can be hierarchical building blocks, and you can share these across projects and across uh, team members. So this is very important if you're doing complex design. You really need this feature. It's something that KiCad does not yet have on its own, but when combined with Confirma, you get this, and it's an important feature. It's something I wanted to show. So you can do very complex design now using KiCad front end. Uh, so, all right, looks like our simulation finished up here. Let's go ahead and close that, and then we'll view the results and see if we can figure out what we're looking at. So let's hit the viewer. Okay, that's some intermediate result I had here. Let me pull up a refresh and pull up the probe. Okay, so let me look at the top level schematic and see what we're going to look like. So we have this B to A converter, and so I believe what we're trying to do is we're trying to create a table-based sine wave generator. So this is the output of the DAC logic output table. So we're going to take that, we're going to plot that. Now that output is fed through an analog filter. So we want to look at that also. So this should be kind of jaggedy and have quantization error. This does smoothing, so we should get like a more analog filtered waveform here. So let's go ahead and take a look. Let's see, what was that called again? Logic output table. Okay, so we're going to say V logic output table, V logic output table. Here we go, and we want to plot that with that filtered one here. I think that's the guy here, I believe. All right, so let's plug these together. Okay, so that looks very good. So this is the D to A output, and then this is the filtered output. So there's a little bit of delay, time delay in the filter, but it all looks as expected. Okay, so let's see here. So wrapping up. So what we've done is we've looked at a transistor level analog design, simple one, but you can do complex ones, no problem. Um, and we've also looked at a behavioral digital mixed signal with some analog circuitry in there. All that worked just fine. We've switched between a variety of simulators. You can see how quickly and easily it is to switch between um, top level test benches. Um, Turns out that you can have multiple instances of Confirma running also. I won't get into that. There's other tools to talk about. I'll talk about on another in another video or something, but it's kind of exciting actually. There's a lot of things coming. There's a lot of work to allow for RF and microwave design in standard SPICE simulators. So we have things like T-line calculators, microstrip calculators, and transmission line stuff. We have models already implemented for microstrip and SPICE simulators. We're still working on that. There's some other things coming. There's interfaces to a variety of layout tools. So one of the layout tools I like to use is Lazy. It's a university tool. It works very well. I've done layout in Lazy and then have been able to pull Lazy GDS into Cadence, for instance, and get it to pass LVS and DRC checks. Not too hard, took a little work, not too hard. Once you got it set up, it works just fine. We've also used LEdit, some other tools. We've done LPE simulations using extracted netlists in Calibre. So you can do view switching in Confirma, and you can co-simulate schematic views with layout parasitic views. So that all works fine. So there's still some work to do, but it's coming along. Hopefully we'll get it out there soon. Again, I don't know yet what the distribution channel will look like. So check back once in a while, see how things are progressing over here. But hopefully it'll be out in the world soon, and then everyone can have their own personal IC design tool suite, one that you can maintain yourself and one that's easy to use, and you can keep it with you and develop your own design portfolio throughout your career. Something I think is very powerful. You can do personal development if you want to get into new areas of design. you want to design synthesizers or something, you have a framework to do that in before you actually have to do it for work or something like that. So, all right, well, I went on much longer than I thought I would, but thank you very much for sitting in. I hope you found it interesting. Check in once in a while. Thank you for your attention. Bye bye.